So as we wrap up chapter 1 today, we're going to see why these limits, what the purpose of them, why we've been working so hard on them, how they lay the groundwork. This is the last official lesson of pre-calculus, okay? Starting on Monday, we will officially be in the world of calculus, and from then on, there's no looking back, all right? We're only going forward. But we want to see what do limits have to do with this idea of continuity and why are they so important? It's key for you to walk out of here today with an understanding of the difference between the word instantaneous and the word average. That's going to be a really important takeaway for today. And if you are taking a physics class or have taken one in the past, you will see the beginnings of the connections to velocity. We'll also connect to acceleration, but we'll start with velocity today. All right. Let's start with defining the average rate of change. This idea of something being average does not require calculus. In fact, you start learning this in Algebra 1. The average rate of change is the same thing as the definition of slope. These two things are equal to each other. You learned to define slope back whenever you learned Algebra 1, whether that was in middle school, 7th grade, 8th grade, whenever you learned slope, you were learning the average rate of change. And so, give me what you remember about slope. What is that? That's the slope-intercept of a form, and they use the letter m for it. But what's the formula for figuring out the slope in the first place? Okay, I'll take that. y2 minus y1 over x2 minus x1. So, Tyler, what do you need in order for that formula to work? You need 2 points, okay? And that's the idea, is the average rate of change requires 2 points in order to be able to find those. We're going to less often use y2 minus y1. We will more frequently use this, f of b minus f of a over, and what do you think the x values would be then in the denominator? Okay, f of b means the x value was what letter? B. And f of a means the x value was a, okay? So for the average rate of change, you don't need calculus, you just need 2 points. And that is what we define as being the average. Okay, point A, point B, what is the average between the two? So here's an example of a easy question, or it should be, that doesn't require any calculus. Find the average rate of change along the parabola from the interval -2 to +4. And so as you calculate that, the average rate, you'll be doing f of 4 minus f of -2 over 4 minus -2. That's the average rate of change. So you need to know what the 2 points are first, so maybe you'll do a little scratch work on the side to figure out what those 2 points are. If you plug in f of -2, I'm going to get 2 times -2 squared minus 3 times -2 plus 7. So that's 8 plus 6 plus 7. So who's got that for me? 21. Whoops, that's the... And then we'll also need f of 4. So that'll be 2 times 4 squared minus 3 times 4 plus 7. So that's 32 minus 12 plus 7. 32 minus 12 is 20 plus 7. So I get 27 minus 21 over 4 plus 2. So we're looking at 6 over 6. So the average rate for this particular interval is 1. That means the slope that connects point A to point B is 1. Okay, so hopefully you can picture that. This is the graph of a parabola. Okay, we have point A, we have point B. The slope that connects the two has a slope of 1. That's what we're finding. That is the average rate of change. So slope equals average rate of change. But it's just the slope connecting the two. You don't need calculus for that. what you need calculus for is when you want to find the slope at one point on a curve. Okay? And so let me just draw you an example. So that would be finding the spot where, see if I can get it just right. See how I just had one point, but the slope is the same? That's what we're going for in calculus, to find the slope at one point instead of the slope at 2 points. Okay? And you can't do it without calculus. All right, so the slope of a line. Kind of divide the slope of a line is f of b minus f of a over b minus a, and just put a thing that it requires 2 points. The slope of a curve. Is also f of b minus f of a over b minus a, but it has a limit in front of it. And what we want to do, I'm going to kind of move back to my drawing here on the board. We want to move A in this direction, and we want to move B in this direction until they meet each other. And they are on the same position, and they meet each other at that spot right there. So our limit is going to say that B approaches A. Okay, B approaches A. What's going to happen to the denominator if B approaches A? Can you think about that?
0.
Okay, I'm going to get 0 in the denominator. But never fear, we've just spent the last week and a half learning how to deal with limits and what do we do when we have 0 in the denominator. Okay, so that is, so this only needs 1 point. All right, in calculus, we often want to define the rate. Okay, that word rate in your mind needs to start becoming synonymous with the word slope. Okay, we use the word rate in calculus, but those two things are the same. We want to describe the rate at which the value of a function is changing with respect to its x value to be the slope of the tangent. Now, tangent in this case does not mean the trigonometry tangent. This is not TOA, like opposite over adjacent tangent. The definition of tangent is a line that skims off a function and intersects only once. You've seen that in geometry where you had a circle and they defined a chord as being a line, something that intersected a circle twice, and a tangent being something that intersected a circle once. Okay, that is called a tangent line, and so something that intersects only one time. All right, we call this in calculus the instantaneous rate of change. It only requires 1 point. Only requires point A and not both point A and B. So we're able to narrow it down to a moment in time. So for example, say you went on a road trip from here to Vegas. You might calculate your average rate of change for the entire 4.5 hour trip. Okay, so what was the average, including the times I had to go slow on the 91 because of construction or traffic, and then including the times I got to go 80, 85 out in the desert, like what is my average? As opposed to the instantaneous being what was my speed or my rate at 8:14 and 37 seconds. At that moment in time, what was my speed right then? That's the difference we're talking about here. Okay, so given this function, find the instantaneous rate of change at x equals -1. Okay, so we are going to set up the limit, as a approaches -1. B, I was right the first time. So we're going to have f of b minus f of -1 over b minus -1. So we only have one point to work with. We don't have both points to work with, we only have one. Never fear, it's all going to work out fine. Remember to keep your equal sign going as long as you have a variable in the problem. So your equal sign would be first. Your limit notation would be next as long as we're working with a variable. So f of b means plug b into the equation. When I plug b into the equation, I get b squared plus 2. Minus f of -1. And what do I get when I plug -1 into the equation? I get 3. My denominator turns out to be b plus 1. Kind of made that a little longer than I needed it to be. Okay. All right, we keep going. We connect our work with an equal sign. We're still working on limit. We still have variables. What does my numerator turn into? B squared minus what? 1 over b plus 1. There's more algebra to be done. We talked about all those algebraic strategies. Will we be doing factoring? Will we be doing common denominators? Will we be doing dividing? So this is an opportunity for you to factor. The numerator will become b minus 1, b plus 1 over b plus 1. Now it can reduce. I still have limit because I still have a variable, and I use parentheses because that's what I had left. I had the factor left. Now is the final time where I can drop the limit notation because I'm going to replace the value of b with -1. So I'll have -1 minus 1, and that is -2. So what that means on this parabola is that the slope, which is also called the instantaneous rate of change, at this moment is -2. It will never be -2 again. Anywhere else on the parabola, the slope will never be -2 again. Let's take a look at that. Can you sketch a parabola right here? Okay, there's a sketch of the parabola. -1 is about right here. The little tangent that would go right there, that's going to have an instantaneous rate of change, or a slope right there is -2. Nowhere else on the parabola will there ever be a slope of -2. That's the difference between a line, right? A line, no matter where you are on the line, the slope is always the same as it was before. The slope of a line never changes, but the slope of a parabola changes everywhere. Every single point has a different slope. So what if I had put a point over here? What would you expect the slope to be? What kind of a number? I would expect it to be positive because it's over on that side. Okay, what if I'd put the point right here? What would you expect the slope to be? I would expect the slope to be 0 because the tangent C is completely horizontal. But there will never be another point with a slope of -2. You found the one. Okay, let's do another one. Find the instantaneous rate of change for the volume of a cube at x equals 3. Now, I didn't give you a formula to start with. I'm assuming that you know that the volume of a cube equation is x cubed. I'm assuming that you know that. If we want to find the instantaneous rate of change, we'll be doing the limit as b approaches 3. And we'll do f of b minus f of a over b minus a, approaching the number 3. Okay, so my numerator is f of b, which means plug b into the volume equation, and we get b cubed. Minus f of a, which is plugging 3 into the equation, so we get 27. And then the denominator would be b minus 3. Now I don't want to plug 3 in again right now because I'm going to get 0 in the denominator. I want to factor first. So in the last problem, we were using the difference of squares. What do we call this one? Difference of cubes. Now we've seen it in one of our homework assignments before, homework problems before. Okay, how do we factor the difference of cubes? So if you don't remember, you might want to write this down. Okay, if you have b squared minus a squared, that's going to be b minus a, b plus a. That's the difference of squares. The difference of cubes, if you have b cubed minus a cubed, it still starts with b minus a. That's the format. But the rest of it is all positive. It's b squared at the beginning, a squared at the end, and ab in the middle. Okay, that is the factoring pattern for the difference of cubes. So I can apply that to this limit. So my first one will be b minus 3. My next one should start b squared, and the end should be 9, because that's 3 squared. What should be in the center? 3b. Okay, that is the factor pattern for distance of cubes, and my denominator is b minus 3. So now I can reduce. Reduce, reduce. What I get is still a limit with parentheses, b squared, bless you, plus 3b plus 9. And now I can plug the number 3 into here. So I'm going to get 9 plus 9 plus 9, or 27. Which means the instantaneous rate of change for a cube at that moment, for the volume of the cube, is 27. Okay, I like to imagine this as a cube. Imagine it like an ice cube. And the ice cube is melting. And so sometimes it starts out melting really slowly, but at any moment in time it's going to melt real fast, especially when you get to the end. That end of my ice cube melts really quickly. All right, this one gets a little trickier because look at it's a little bit more of a complicated equation. Find the instantaneous rate of change at 1. So b has to approach 1. And I'm going to do f of b minus f of 1 over b minus 1. All right, the numerator with the limit notation is going to start out with me plugging the letter b in. So 1 minus b over b. Minus me plugging the number 1 in. What do I get when I plug in the number 1? And then my denominator is b minus 1. All right, so then we have b approaching 1, and the numerator is 1 minus b over b, and the denominator is b minus 1. Remember, it gets really awkward in algebra when you have a fraction within a fraction. So what's the way we want to get around that? Instead of having 1 minus b as a numerator and then having a single denominator of b and then having another denominator of b minus 1, how do we get around that algebraically? Andre? Yeah, that's going to be a much better way for you to approach that. So you're going to want to multiply this by the reciprocal. So this should turn out looking like 1 minus b over b multiplied by the reciprocal of 1 over b minus 1. Now, is this a reducible? Okay, well, let me back up. Hopefully we learned from the quiz, this is not an opportunity for us to use common denominators. Okay, that's not what we're going for here. We're going for reducing. Okay, any ideas? Is this a reducible problem? Noah says yes. Why do you think so? Now she's not sure.
You could multiply or have the denominator be negative 1 minus b.
Has something to do with negative 1.
1 minus b.
Yeah, it does definitely have something to do with negative 1. This is how I would recommend that you think about it. Okay, this b minus 1 minus b here. Okay, if you factor a negative 1 out of that, we've seen that we've done that before. We did when we were doing translations. You factor the negative out. Then it's in a better order. Then you can reduce. Okay, we've seen that before when we had 3 minus x. If you factor a negative 1 out, then it can become x minus 3. Once you do that, you can reduce. So what would be left in the numerator here? Yeah. And the denominator is simply b, which means now I can plug in negative 1 over 1. So my instantaneous slope, or my instantaneous rate of change, is negative 1 along this. This is a hyperbola. Along this hyperbola. Okay, in physics, we now use, instead of x, we use t. What does t stand for in physics? Time. Okay, the idea is still very, very much the same. Okay, I want you to look at, in physics, they do t plus h. That's their b. And this is their a. Okay, so we're going from point A to point B. In other words, we're going from time being A, or being time, and then time plus h. In physics, you want those two moments in time to be like instantaneous. So how big does h have to be if those two moments in time are going to be as close together as humanly possible or mathematically possible? That one, I mean, 1 second away, that's way far. I mean, in physics world, 1 second, a lot happens in 1 second. Try jumping out of an airplane, okay? A lot happens in 1 second, okay? So, or try, crashing a car. Like, a lot happens in 1 second. So we don't want it to be h to be 1. What do we want h to be?
0.
As close to 0 as possible. Okay, so in physics, they set it up as h approaching 0 instead. It's the same idea, though. It's time 1 to time 2, but we want those times to be so close together. And then the denominator doesn't need a subtraction anymore. I mean, it has it. It's h minus 0, because that's how close they are, but h minus 0 is nothing. So in physics, you'll see it set up like that. It's the exact same concept. Okay, the exact same concept. So actually, I want to, can you guys duplicate a slide on yours? Do you have the capability to do that? Okay. Go back to, because we have the time to do it, go back to this first one that we did and duplicate it, and we're going to do it like the physics way. And I'm going to show you get the same answer no matter what. So go ahead and duplicate slide 7. And we'll do it together. What was it? X squared plus 2. And then instead of being x equals negative 1, make it time equals negative 1. All right, so let's pretend we're doing this in moments of time. So the definition in physics would be f of t plus h, okay? But we know what our time is. Our first time is -1. So let's say it's -1 plus h minus, and then f of -1. So that's our time 1 and our time 2. You could even, you guys know how to do subscripts in physics, right? Like if you do t sub 1, you've seen that in your physics classes. And so then t sub 2 would be -1 plus h. That would be like, I'm starting with time 1 and then, so it's another way to think of it. All right, we want h in our denominator, h minus 0, and h approaches 0. I usually just kind of just don't put minus 0. Okay, let's work this out. It's going to work out to be exactly the same. The limit as h approaches 0. So f of -1 plus h means plug -1 plus h in parentheses into the equation. So you're taking all of these parentheses and you're plugging it in to the equation. So that's going to give me -1 plus h squared plus 2. Minus, I take -1 in parentheses and I plug it into the equation. So that's going to give me -1 parentheses squared plus 2. But I'm subtracting that whole group. So I put an extra set of parentheses around that set. Okay, that whole second half is getting subtracted. All over the denominator, which is just h. And now we FOIL, and we do some algebra. So when I FOIL -1 plus h, quantity squared, I get positive 1. I get minus h, and then I get positive h squared, plus the 2. And then minus how much? 3, because that's what's in that parentheses, is 3. Still all over h. All right, let's keep going. Okay, what happens in that numerator? Can you clean it up for me? Well, what should lead the numerator if I'm putting everything in the right order? H squared. What should come next? Minus 2h. What should come next? -2. Where's -2? Yeah, I've got 1 plus 2 minus 3. Okay, so those all are gone. So I really just have h squared minus 2h over h. Okay, great. I did a lot of work towards simplifying. Now what?
Factor out the h and everything.
Yeah, factor. H comes from out from h minus 2 over h. Now what? Reduce. And then finally, oops. In parentheses, h minus 2, plug in 0, 0 minus 2, answer's -2, same as I got the other way. Yeah?
Why can't you just reduce at the step of h minus 2? Like instead of having a factor,
If you're confident in your ability to reduce without making a mistake,